Hello, my name's Chris Mack. I'm a gentleman scientist. If you don't know what that means, you have been studying 19th century scientists. But I work in the field of lithography, have been for almost 30 years. Hard to believe it's been that long. My specialties right now are in the study of line edge roughness, the kind of stochastic variations that inflict itself upon small features, these 20 nanometer and below features that we're trying to print in lithography today. It seems to be the ultimate limiter to resolution, so an understanding of line edge roughness is critical to marching down Moore's law and printing that next small feature. Moore's law progresses down step by step in an incremental way, and yet every now and then we need big jumps to keep us going. Yet the heart of how we make these improvements is with incremental improvements and incremental change. So there's always a continuous improvement efforts going on to understand things and control things just a little bit better. But in the background, we're working on some disruptive change, some major thing that we can do. So most of us in the industry spend their time working on some or the other or both at some time in their career. The semiconductor industry has been relying on lithography at the 193 nanometer wavelength for a number of years now. We've made the transition to immersion lithography with the high index water, allowing much higher resolutions. And we've been milking that cow for a long time, and it's been great. Making a lot of money, printing really, really small things, but there's a limit. There's only so far you can push this 193 wavelength without doing exotic things like double patterning, which we're already doing, to quadruple patterning, which is something we might do, but it's very expensive. So there's a hope that we can jump out of the 193 wavelength paradigm into something major that's different. There's a number of contenders. We call them next generation lithographies. EUV is the one receiving the most attention and the most money right now. It's been under development for over 20 years. There's a lot of engineering talent and money going into the development of tools, materials, processes to enable EUV lithography at a 13.5 nanometer wavelength. But there's other alternatives as well. Multiple E-beams. Electron beam lithography has had high resolution for decades, but it's slow. It's a serial, one at a time pixel writing technique. So we can't do mass production with it unless we can use multiple E-beams all at once. So there's a huge effort to create hundreds of beams, thousands of beams, millions of beams, all exposing in parallel to get both high resolution and high speed. It's a daunting engineering challenge, and we're still not there yet. There's a couple of different companies, research groups working on the development of these tools. It's unclear whether or not they're going to be successful, but it's an alternative to EUV. The other alternative is to somehow use the physics of self-assembly to build up from the bottom up very, very small features of specific sizes and shapes. Directed self-assembly means we can put these as self-assembled materials in exactly the place we want them, and that's a requirement for lithography for semiconductor manufacturing. So the combination of 193 immersion, lithography to create template patterns that self-assemble molecules then grow up from is a very exciting opportunity. People are working very hard on it. It's very exciting. We're worried about defectivity, whether or not we'll be able to build these patterns, say, 1 billion little holes where not a single one of them is wrong or missing on a chip. That kind of defectivity levels, 1 out of 1 billion or 1 out of hundreds of millions, is what we need to be successful. And of course, we haven't demonstrated that yet. Still a long ways to go, but it's also a very exciting opportunity for research today. If you want a new technology to make it in this industry, 3 things have to happen. You only get 2 of them, it doesn't work. The 3 things are the performance and quality of the result. So do you have the resolution? Do you get the right line edge roughness? The right pattern placement? The quality factors in lithography. Number 2 is the cost, the economic factor. Can you print it at the right cost? Remember, Moore's law is about lowering the cost per function, not about making smaller things. We need to build things that are cheaper and therefore integrate more inexpensive components onto one piece of silicon. That's what Moore's Law is all about. So if you don't hit the economic factor, nobody wants to do it. Nobody even wants to think about doing it in this industry. And the third thing is timing. This industry marches to Moore's Law. We move step by step together, an entire industry, to enable these advances. If you don't give the right technology at the right time, it doesn't matter how good it is. If it's before its time, if it's after its time, it's not going to be used. So timing is the third thing. And you have to do all three to be successful. The end of Moore's Law has been oft predicted, and I'm loath to make a prediction as to when it might come to an end. However, it must, and it will. Moore's Law has made several transitions. In the early days, it was about scaling up, adding more transistors onto a chip. Over time, Moore's Law transitioned to be scaling down. It's about shrinking feature sizes, making transistors smaller so that they're cheaper, faster, and smaller. But Moore's Law can and will make another transition. It will transition into integration, where we integrate more and more features onto our chip. Silicon photonics, MEMS, actuators, sensors, 3D integration of memory and microprocessors onto one chip. These kinds of scaling out will be replacing, in my opinion, the scaling up and the scaling down. So the Moore's Law scaling down will come to an end, and it probably won't be that far in the future when it does. But that doesn't mean innovation in the semiconductor industry is over, not by a long shot. Moore's Law will continue, but in a very different way.